I'm Dr. Michio Kaku, professor of theoretical physics at the City University of New York and author of a new book entitled Quantum Supremacy, about the rise of quantum computers.
Chapter 1: Quantum Computing.
Well, some people ask me, why are you interested in physics? And my answer is, how can you not be interested in physics? I mean, we're only talking about the universe. We're only talking about the fundamental laws that drive the entire universe. So for me, it's hard to understand how people are not fascinated by stars and galaxies and black holes, how people cannot be fascinated by the way the universe is put together. I first became interested in physics when I was 8 years old. I still remember that all the newspapers were stating that a great scientist had just died, but on his desk was the unfinished manuscript of his greatest theory. Well, I was fascinated. What could possibly be so fantastic that a great scientist could not finish that book? I had to know what was in that book. I went to the library and I found out this man's name was Albert Einstein. That book, which he could not finish, was to be the theory of everything, an equation perhaps no more than 1 inch long that would allow us to, quote, read the mind of God. Well, I was hooked. I had to know what was in that book, and can I contribute? Well, today the leading candidate for this theory of everything is called string theory, and I'm the founder of string field theory, one of the main branches of string theory, in an attempt to find this fabled equation. And the key may be quantum computers. As a physicist, I work in trying to complete Einstein's dream of a theory of everything, an equation perhaps no more than 1 inch long that would allow us to, quote, read the mind of God. But that requires enormous computer power in order to solve this fabulous equation, and that's what drew me into quantum computers. Only quantum computers are powerful enough to perhaps one day settle the question of, is there a theory of everything? We all know that digital computers have changed the entire landscape. Nations which can use digital computers are rich, they're powerful, they can communicate, they can revamp the economy. However, we're now in the initial stages of the next revolution. The next revolution will be quantum computers that will make the digital computer look like an abacus. In other words, the future of digital computers is to wind up in the garbage can. We're talking about a new generation of computers, the ultimate computer, a computer that computes on atoms, the ultimate constituents of matter itself. Quantum computers have the capability of changing every aspect of our life, the economy, health, transportation, everything could be changed by quantum computers. Take a look, for example, of food supply. We rely upon fertilizers. There was a green revolution that took place that allows us to feed the population of the world. But that green revolution is slowly coming to an end. We need a second green revolution, being able to take nitrogen from the air and combine it to make ammonia and fertilizer. And already, we're trying to use quantum computers to unlock the secret of how to make fertilizer from nitrogen. Also, take a look at energy. Fusion power could one day give us unlimited energy almost for free. We're talking about an energy source where the basic fuel is seawater. Fusion plants burn seawater, the hydrogen of seawater, to create fabulous amounts of energy without nuclear waste, without the threat of a meltdown. And quantum computers may be essential to stabilize the vacuum and hydrogen so that they don't cause an accident or they don't fall apart. So in other words, quantum computers can affect the economy in basic ways, not to mention medicine. We create medicines by trial and error. We create hundreds of chemicals and test them one by one in a petri dish. This is old-fashioned, slow, but that's all there is. That's all we can do. In the future, we'll be able to model diseases at the molecular level. We'll be able to do molecular experiments in the memory of a computer rather than in a petri dish, trying to look at hundreds of chemicals to find out which one is medically relevant. In other words, we're talking about turning medicine upside down. The question is, who's involved in this race to perfect quantum computers? And the answer is everyone. If you're not part of the race, you could be irrelevant in the future. All the big names of the computer industry, Google, IBM, Honeywell, they're all in the game because they realize that you could become irrelevant. Wall Street is always looking for the next big investment, and this could be it. All of a sudden, we have companies that just started a few years ago becoming multi-billion-dollar companies as they try to put their flag on the mountain of quantum computers. This is now big business. This is one of the hottest stocks that are available on the stock market now. In other words, it's a race. All the big players in Silicon Valley are part of this race because if they're not, Silicon Valley could become the next Rust Belt. We have something called Moore's Law, which says that computer power doubles every 18 months. We take it for granted. Every Christmas, your computers are twice as powerful as the previous Christmas. The economy is based on that. But Moore's Law is falling apart. Moore's Law is getting slower and slower. Finally, it'll flatten out. And let me ask you a question. Would you upgrade your computer knowing that it's just as powerful as the last few generations of computers? No. This could cause a depression in the computer industry. We physicists called attention to this decades ago, but we said that, well, we still have a few more decades left, but it's coming. It's coming because transistors are getting smaller and smaller. A transistor today could be, let's say, 20 atoms across. When you start to hit 5 atoms across, then electrons can then hop across and create short circuits. And Moore's Law comes to an end. We're now gradually approaching that limit. When you look at the curve of the exponential growth of computer power, it's quite remarkable. This is where modern technology has taken a leap, but now we're beginning to level off, just like we predicted because of the quantum theory. Electrons are not dots. Electrons are waves, waves of probability, and they're unstable if you start to get electrons and then analyze them at the level of an atom. So in other words, Silicon Valley has to confront the fact that Moore's Law will eventually collapse. So for all these reasons, we have to go beyond digital computers to atomic computers, computers that compute on atoms rather than on transistors. Right now, anyone who's interested in security is interested in quantum computers, because quantum computers, in principle, have the power to crack any digital code. Think about that for a moment. All the data that is sent on the internet is coded. National secrets of nations are encoded in these codes, which often require you to factorize very large numbers. But that's what quantum computers can do. They can factorize very large numbers and thereby crack almost any code that is based on digital technology. That's why the FBI, the CIA, and all national governments interested in computer security are following this very closely. So for example, let's say you want to have a secret that's encoded. You put a code on it, and the code says you have to factorize a digit that is, let's say, 50 digits long. It would take perhaps a few hundred years for a digital computer to factorize a number that is 50 digits long. A quantum computer may be able to do that almost instantly. And so you see the anxiety that this is being created for people involved with computer security. You're not talking about being able to break into any other computer on the earth that is based on digital technology. Now, we're not there yet, so you don't have to worry that someone's going to steal all your secrets tomorrow, but it will come. And when it comes, we're going to have a major revision of how we code our most treasured national secrets. Ordinary digital computers compute on zeros and ones, zeros and one. But if you take a look at medicine, if you take a look at energy, you take a look at molecules, they're not based on zeros and ones, zeros and ones. They're based on electrons. And electrons can be smooth, not zeros and ones, zeros and ones. And these electrons, how come they have so much computational power? Because they could be in two places at the same time. Now, at this point, you may say to yourself, that's ridiculous. That's stupid. How can you be two places at the same time? But that's exactly what electrons do. Electrons can be multiple places simultaneously at the same time. That's what gives quantum computers their power. They compute on parallel universes. Not just one universe, the universe that we're accustomed to, but an infinite number of parallel universes. Now, this sounds like something from Marvel Comics. But then the question is, where did Marvel Comics get this idea? Marvel Comics got this idea from quantum physics, because the fundamental basis of quantum physics relies upon the fact that the electron can be in multiple places simultaneously at the same time. One of the big goals of quantum computers, not just creating new forms of energy, new products, new forms of transportation, but perhaps unlocking the secret of life itself. You realize that life is based on molecules, not zeros and ones, zeros and ones. Molecules that in turn can create Alzheimer's disease, Parkinson's disease, cancer. These diseases are beyond the reach of digital computers. But hey, this is what quantum computers do. They work with molecules, they work with atoms, they work with electrons. And that's why we hope that one day we'll be able to cure the incurable using quantum computers. Now, some people say, won't that put doctors, chemists, and biologists out of a job? Won't they be on the unemployment line because we don't need them anymore? No. In the future, the people on the unemployment line will be chemists and biologists who do not use quantum computers. The winners of this game will be biologists, chemists, mathematicians who use quantum computers in the same way that a carpenter uses a hammer. A hammer does not replace the carpenter. The hammer simply increases the power of the carpenter. And that's what quantum computers will do for medicine, transportation, energy, you name it, quantum computers will be there. If you look at life itself is driven by at least two types of molecules. One, of course, is proteins that make our muscles, make our body. And the second is DNA that has the instructions by which to create new forms of life. Quantum computers operate at the molecular level. They allow you to predict different kinds of proteins, how DNA is going to interact without actually building a DNA molecule. You could do it in the memory of a computer. Now, what can digital computers do for this? And the answer is almost nothing. Digital computers can only count zeros and ones, zeros and ones. They cannot simulate the motion of molecules inside DNA and inside a protein molecule. That's where quantum computers come in. Life is quantum mechanical. Life is not based on zeros and ones, zeros and ones. So how long will it take for a digital computer to simulate life? And the answer is forever. You can't do it. You cannot simulate the basic chemistry of DNA and proteins on a digital computer. That's where quantum computers come in, because life itself is based on atoms and the quantum principle. Computers go all the way back to prehistory because we had to count things. As we primitive peoples became more prosperous, we had to count how many cows we had, how much grain could be harvested. We had to count these things, and that began the beginning of analog computers. Analog computers could be based on sticks, bones, levers, gears, pulleys, whatever it took to count how many cows you had, to count how much profit you made. So this went on for thousands of years until finally we reached the work of Charles Babbage. He creates the ultimate analog computer with hundreds of gears and levers and pulleys, and by turning the crank, you could then calculate longitude, latitude for ships. You could calculate interest rates. It was very valuable to have an instrument like that for the banking industry, for commerce. But then World War II comes along, and at that point we realized that Babbage's machine is simply too primitive to defeat the Germans. The Germans, of course, had their own secret code, and we had to break it in order to win World War II. So the job was given to mathematicians like Alan Turing. Alan Turing was the one who codified a lot of the laws of computation into what is called a Turing machine. He basically introduced the power of logic and mathematics to reduce computation to a simple series of manipulations. Every computer on the earth, every digital computer, is a Turing machine. And of course, it's digital. It operates on zeros and ones, zeros and ones. But then we went into the quantum era with Richard Feynman. Richard Feynman was a Nobel Prize winner, but he was also a practical joker, as well as one of the founders of quantum electrodynamics. For example, he worked on the atomic bomb. But as a prank, he got a sheet of paper and wrote something like, "Guess who?" question mark on that sheet of paper, put it in the safe, and sealed it up. Well, the next day, the authorities opened that safe and found the message, "Guess who?" There was panic at Los Alamos. Some spy had gotten the secret of the atomic bomb and was basically toying with the authorities. Well, that's Richard Feynman, practical joker, but also a visionary. And he asked himself a simple question: how small can you make a transistor? That's a simple statement, right? Transistors control the flow of electricity. They're either off or on, open or closed. That's called a transistor. And then he said, how small can you make a transistor? And he realized that the ultimate transistor is an atom. One atom that could control the flow of electricity, not just on or off, but everything in between. As we mentioned, if this is an atom, it can spin North Pole or it can flip in the South Pole. This is how transistors work. Transistors are either open or closed to electric current. But atoms can spin in any direction simultaneously. That's the power of quantum computers. They compute not on zeros and ones, but everything in between simultaneously. That is incredible. For example, let's take a mouse and put a mouse in a maze and let a digital computer calculate what happens when a mouse is in a maze. Every time the mouse hits a juncture, it has to decide left or right, left or right. And then it goes to the next juncture and has to decide left or right. Very tedious, very slow, but that's how a digital computer analyzes a mouse inside a maze. Now, how does a quantum computer analyze it? It looks at all possible left-rights, all possible paths of the mouse simultaneously, instantly, analyzes all of them all at once. So how much faster is a quantum computer over a digital computer? In principle, infinitely faster. Think about that. We're talking about a new revolution in counting, able to count hundreds, thousands, millions of paths instantly at the speed of light. Something which our bodies do, we call that biology, medicine. Our atoms, our hormones, our proteins do that all the time. But we, using digital computers, calculate with zeros and ones, zeros and ones, zeros and ones, a tedious, slow process that Mother Nature does not use at all. Mother Nature is smarter than us. So you would think that after World War II, he would be heralded as the hero that saved the lives of hundreds of thousands of people that helped to defeat the Nazis. Nope. His work was classified. It was considered too sensitive to be released to the public, and it's a very sad story. One day, somebody burglarized his house. He called the police. The police investigated his belongings and realized that he was gay. As a consequence, he was arrested, and he was tried and sentenced. For punishment, he was injected with hormones that made him grow breasts and feminized him, changed his whole body. Of course, Alan Turing was very much mentally destabilized by this, and one day they found his lifeless body because apparently he committed suicide. And next to him was an apple laced with cyanide poison, an apple that he ate to commit suicide. And so some people think that the symbol of Apple computers is that apple. The apple that we all have on our laptops and our Apple hardware could be a memory of what Alan Turing did to the field of artificial intelligence and the digital computer. He saved the lives of hundreds of thousands of people, and yet he was totally unknown to the British people. Well, Alan Turing also pioneered artificial intelligence. He said that people who work with artificial intelligence are barking up the wrong tree. There's no definition of artificial intelligence. So he came up with a test rather than a definition. You put a human in a box, you put a robot in a second box, and you are allowed to ask any question you want to see which box contains the human and which box contains the robot. This is the Turing test. It's been done many times, and so far, every time, the Turing test has not been able to fool a human. Every time this test has been done, eventually humans can ask a question that'll trip up the robot, and we say, aha, there's a robot there. But Turing said that it's only a matter of time before one day a robot passes the Turing test and becomes indistinguishable from a human being. Well, we'll wait and see. It's a tragedy of history that the father of artificial intelligence and the father of the electronic digital computer is pretty much unknown. We celebrate, of course, the people who built the atomic bomb, but what about the man who pioneered the digital computer and artificial intelligence, Alan Turing? Well, that's why I was pleased when the movie came out, The Imitation Game, the first Hollywood movie that allows people to understand the tears, the sweat, the toil that went into creating the computer revolution. We tend to think that an advanced computer is a modern technology because, of course, it involves so many calculations, so intricate, but that's not true. 2,000 years ago, there was a shipwreck, and in the boat that sank was a device that was encrusted with coral and dirt. But when you brushed away the dirt and debris, you began to realize that it was a machine of incredible complexity. It was, in fact, a computer. This amazed the work of archaeologists around the world. It was the world's first analog computer, and it was designed to map the motion of the moon, the sun, and the planets, to map the motion of the known universe. Now, Charles Babbage is sometimes called the father of the computer because he built this gigantic machine that, when assembled, actually weighed several tons. You turned the crank and allowed you to make enormous calculations, longitude, latitude, interest rates, things like that. But somebody went one step beyond that. Lady Lovelace was a member of the aristocracy. She had a background in mathematics, and she was curious about this machine that was being built by Charles Babbage. And she realized that a machine of this complexity, you have to have instructions for it, because you don't want to just calculate one number. You want to calculate a series of numbers that give you the answer to a problem. For that, you have to have instructions. These instructions are called a program. And so in some sense, Ms. Lovelace was the first programmer programming an analog computer to crank out not just one number, but as many numbers as you want by following the rules of a program. So she was the world's first programmer. Now, the digital revolution is based on transistors. So what is a transistor? A transistor is a valve. When you turn the valve, then you allow electrons to flow in a pipe. Think of the water in plumbing to be electricity and the transistor to be a valve. With a little bit of turning the valve, you can shut off the water completely or leave it open. The valve can give you zeros or one. One means water can flow. Zero means you turn the valve, you shut off the pipe, and water doesn't flow at all. So that's how plumbing and transistors are very similar. Plumbing allowed you to control the flow of water in a well-structured way. That's why transistors are so powerful. But transistors are based on zeros and one. Zeros and one. Reality is not. Reality is based on electrons and particles, and these particles in turn act like waves. So you have to have a new set of mathematics to discuss the waves that make up a molecule. And that's where quantum computers come in. Because quantum computers are not just off and on, off and on. We're talking about electrons that can spin in any orientation simultaneously. That's why quantum computers can simulate quantum devices. And the most intricate quantum device is you. You are the byproduct of quantum mechanics. If you turned off quantum mechanics, what would happen to your body? It would dissolve. It would dissolve into a bunch of random subatomic particles. What holds these particles together? The quantum principle. Quantum mechanics holds your atoms together. It holds your body together. It allows your atoms to interact with other atoms, to create catalysts, to create DNA and proteins. So what has quantum mechanics done for you lately? The answer is everything. At the fundamental level, quantum mechanics can be reduced down to a cat, Schrödinger's cat. Schrödinger was one of the founders of quantum mechanics, even though he hated this new interpretation of quantum mechanics based on probability. Let's take a box. In the box, you put a cat with a gun. The gun is aimed at the cat. And the question is the cat dead or alive? Well, until you open the box, you don't know. The cat could either be dead or alive simultaneously. Before you open the box, you don't know if the cat is dead or alive. But if the gun goes off, then of course the cat can be killed. You open the box and the cat is dead. But there's also a probability that the cat is not killed by the bullet. You open the box and the cat is alive. So then the question is, and this is the question that split the physics community for decades, what is the cat like before you open the box? And the answer is, it's in a superposition of two states. It is alive and dead simultaneously. In other words, the universe has split in half. In one half of the universe, the cat is alive. In the other universe, the cat is dead. Now that sounds crazy, but hey, get used to it. That's the basis of the quantum theory, that until you make a measurement, the cat can exist in both states simultaneously. In fact, in any number of states simultaneously. Now, when you take a philosophy course, you learn the famous paradox of when a tree falls in a forest and there's no one there to listen to the tree fall, then the question is, did the tree fall at all? Well, this is even worse, because before you open the box, the cat could be dead, alive, playing, jumping, sideways, sick, any number of states before you open the box. Now, why am I mentioning this? Because this summarizes the power of quantum computers. Quantum computers compute on parallel universes. That's why they are so powerful, because the cat is not just in one state, the cat is in all these parallel states simultaneously. Now, Steven Weinberg, one of the founders of modern quantum theory, explained it in this way. When you go into a room with a radio, your radio can pick up all sorts of frequencies, but your radio is tuned to one frequency. Your radio is coherent with one frequency, just one, and that's what you hear on the radio. Now, that room that you're sitting in is made out of electrons. Electrons are also waves. Waves of everything. Waves of pirates, waves of dinosaurs, waves of UFOs and Martians, all of that, all these waves inside the room. But you are only tuned to one frequency. You can only see one reality. You cannot see the dinosaurs. You cannot see the pirates, but they're there. But you cannot interact with them anymore. So this is how we physicists explain the cat problem. The fact that, yes, the cat in some sense can exist in all these different universes, but you only vibrate in one frequency. Therefore, you cannot see the dinosaurs in your bedroom. When quantum computers were first theorized by physicists like Richard Feynman, people thought that, well, it's an academic exercise. Atoms are so small, the slightest vibration can upset the whole calculation, so it's an academic question whether or not quantum computers exist or not. Well, we don't think like that anymore, because now we make quantum computers. This is reality, that we can now play with quantum computers. In fact, you can even download a quantum computer on your laptop. You can actually connect your laptop to a quantum computer created by IBM and Google. And so it's real. So what is quantum supremacy? Quantum supremacy is the point at which a quantum computer can outrace and outperform a digital computer on a certain task. We passed that several years ago. We are already in the realm where for certain specific tasks, a quantum computer can outrace the world's fastest digital supercomputer. We're now in an entirely different realm, a realm where we're actually creating these things. This is no longer a question of speculation. It's a question of a race between the Chinese and many US companies that are jumping into the quantum computer game. When we talk about digital computers, we can measure their power in terms of bits. For example, spin up spin down, zeros and one, would constitute 1 bit. And for a large digital computer, we're now talking about billions of bits that are modeled by transistors. So the number of bits on a digital computer allows you to calculate how powerful it is. The same thing for quantum computers, except now quantum computers talk not just about spin up or spin down, but everything in between. That's called a qubit. A qubit is not just up or down. 1 qubit represents all the possibilities of an object spinning between up and down. The question is, where are we today? Already we're talking about hundreds of qubits that can be modeled by a quantum computer. Very soon, it'll be a few thousand qubits. And just remember that when quantum computers first emerged, the first calculation was 3 times 5 is 15. Now, a child knows that, but 3 times 5 is 15 was done on atoms. That was a huge breakthrough. Now we're talking about thousands. Thousands of qubits can now be modeled with the latest generation of quantum computers. Eventually, we hope to hit 1 million. And so we're talking about exceeding the power of ordinary digital computers. On specific problems, we've already done that. But we want a general machine, a machine that could exceed the power of any digital computer. We're not there yet, but we're very close to it. There are several analogies that explain the power of quantum computers. Think of a digital computer and think of a room full of accountants. Each accountant does one calculation and passes it to the next, and then does another calculation, passes it to the next accountant. A very slow process, but hey, that's what digital computers do. Now, take a look at a quantum computer. In a quantum computer, all the accountants are working simultaneously, not one by one, but simultaneously. And therefore, you know the power of a quantum computer. Digital computers will take an almost infinite amount of time to do what a quantum computer can do almost instantly, because it computes simultaneously on many qubits, not just one after the next, after the next. That shows you the power of quantum computers. Another problem with quantum computers is the question of decoherence. In other words, everything is based on particles like electrons, and electrons have waves associated with them. When these waves are vibrating in unison, it's called coherence. And then you can do calculations of a quantum mechanical nature. But if you fall out of coherence, then everything vibrates at a different frequency. And what is that called? Noise. So that's the number one problem facing quantum computers. You have to reduce the temperature down to near absolute zero, so everything is pretty much vibrating slowly in unison. That's difficult because you need to have super cool liquids and different kinds of technologies to bring down the temperature so that everything is coherent. Now, nature solves this problem. Photosynthesis, for example, is a quantum mechanical process. We still don't understand photosynthesis. It is the basis of all life on the earth, and it's a quantum mechanical property. And we still don't know quite how it works. But Mother Nature can create coherence at room temperature. Amazing. A flower can do calculations that our most advanced quantum computer cannot. So Mother Nature has solved the problem. We have not. We have to use liquid helium and different kinds of supercooled substances to bring down the temperature to near absolute zero. Mother Nature does it with sunlight. Mother Nature is still smarter than us when it comes to the quantum theory. Some people ask the question, well, how will I as a person interact with quantum computers? Well, we have a cell phone, and that cell phone allows you to contact a whole bank of supercomputers to carry out your wishes. So in other words, in the future, you're not going to have a quantum computer inside your cell phone. Your cell phone will allow you to communicate with a series of quantum computers in the cloud. So supercomputation will be done in the cloud, and you'll be able to access that knowledge in your cell phone. My personal hope for quantum computers is that we'll be able to create a theory of the entire universe. I work in something called string theory, which we think is the ultimate theory, the theory that eluded Einstein, the theory that would explain black holes and supernovas and galactic evolution, a theory of cosmology of the entire universe. But the equations are so complicated, no one's been able to crack them. Perhaps a quantum computer would be able to extract real numbers from string theory so that we could then compare it with what we see in the laboratory. And so that would clinch it. So then we would say, aha, this is, in fact, the theory of everything, and here's how to prove it.
Chapter 2, String Theory.
Albert Einstein spent the last 30 years of his life chasing after a theory of everything, an equation, perhaps no more than 1 inch long, that would allow us to summarize all the great laws of the universe. In other words, to quote, read the mind of God. These are Einstein's words. And he failed. He failed because, well, the universe is much more complex than Einstein thought. We have all these subatomic particles now, hundreds of subatomic particles. How are we going to make sense out of the vast diversity of matter we see around us? Well, the leading candidate right now is called string theory. String theory first bursts on the scene around 1968. The Vietnam War was at its height at that point. I remember when that theory first came out because I was in the Army. And there I was, dodging machine gun bullets, going through a maze of grenades and fields of explosives in them. And I was learning string theory for the first time. And I was amazed at its simplicity, its power. But there I was in the Army. When I got out of the Army, then I started to publish in this field because of the promise that it was the theory that eluded Einstein for the last 30 years of his life. String theory is based on music. So in other words, all these subatomic particles are nothing but musical notes on a tiny vibrating string. So this would be an electron, this would be a quark, this would be a Yang-Mills particles. Different vibrations give you different particles, and that would explain why we have so many subatomic particles. What is physics? Physics is the harmonies we can make on these vibrating strings. What are subatomic particles? Each vibration is a subatomic particle. So what is chemistry? Chemistry is the molecules that you can create when strings bump into other strings. That's called chemistry. So then, what is the universe? The universe is a symphony of strings. And then what is the mind of God? The mind of God is cosmic music resonating through hyperspace. That would be the mind of God. Now, some people come up to me and say, Professor, maybe I don't like string theory. Give me an alternative. Well, for you industrious people out there in the audience, there are 3 criteria for the theory of everything. If you can find an equation that satisfies 3 criteria, you will be heralded as the next Albert Einstein. What are these 3 criteria? First, your theory would have to include all of the theory of gravity of Albert Einstein. Statement number 2, it would have to explain why we have so many subatomic particles, hundreds of subatomic particles. Your theory must explain all these subatomic particles. Third, your theory must be free of mathematical anomalies, inconsistencies, divergences. In other words, it must be mathematically usable, testable against the reality that we see around us. If you can come up with a theory that obeys these three criteria, what should you do? You should call me first, and we'll publish together, and we'll share the Nobel Prize money together, you and me. A Nobel Prize waiting if you can find a theory that satisfies just three criteria. Has to explain Einstein's theory of gravity, it has to explain why we have so many subatomic particles, and the theory must be mathematically consistent. If you can get it, you will be heralded as the next Einstein. So what is the leading candidate to rival string theory? Well, the leading candidate right now is called loop quantum gravity. But loop quantum gravity has problems. First of all, it does contain Einstein's theory of gravity, but it says nothing about particles. There's no electron. There's no proton. There's no neutron. Matter as we know it is not there. Loop quantum gravity is a theory of pure gravity with no particles. Therefore, it cannot describe the universe as we see it, because the universe as we see it has subatomic particles, like the electron, like the atom. What are we made of? And so, in that sense, string theory is the only theory that combines Einstein's theory of gravity with a theory of particles. What are particles? Vibrations on a vibrating string. Every once in a while, the newspapers herald the coming of a new theory. Perhaps this is the theory that eluded Einstein. But then you read the fine print. And then 9 times out of 10, the theory that's being proposed is a theory of pure gravity. No electrons, no protons. And that's what kills loop quantum gravity. But here we are, made out of atoms. Atoms have to be part of your theory. And so most of the theories that you see in the papers that claim to be a theory of everything, all you have to do is ask a simple question. Where is the electron in your theory? And you'll find out, oops, none of these theories have electrons in them. In other words, they don't work. One day, a famous physicist, Wolfgang Pauli, gave a talk at Columbia University advertising his version of the theory of everything. Well, Niels Bohr, one of the founders of the quantum theory, was in the audience. Niels Bohr stood up and he said, "Professor, we in the back are convinced that your theory is crazy. But what divides us is whether your theory is crazy enough." In other words, the theory of everything has to be fantastic. It has to be incredible. It has to be crazy. Why does it have to be crazy? Because all the easy problems were picked off. All the easy stuff was shown to be inconsistent, mathematically or physically. The theory of everything has to be crazy. Totally different from anything ever proposed. And that's where string theory comes in. Because string theory is crazy. Everyone who's looked at the theory says, oh my God, this is a crazy theory. So crazy that it may be correct. The main criticism, which has to be taken seriously, the main criticism of string theory is, well, where's the beef? Where are these particles that are predicted by string theory? String theory predicts the electron, it predicts the proton, it predicts the world that we see around us. But, and it's a huge but, it also predicts other particles, particles heavier than what you see around us. So where are those particles predicted by string theory? One idea is that these particles make up dark matter. Dark matter is relatively new. We now realize that when you look at the stars, you look at the galaxies in the universe, we see more than just hydrogen and helium. We see a new form of matter called dark matter, which is invisible, but there it is in outer space. We think that the next octave of the string is dark matter. But we can't prove it yet, because we don't have dark matter in a bottle. One day we'll have dark matter in a bottle created by our particle accelerators, and then we'll test it to see whether or not dark matter is the same thing as was predicted by string theory. So that's the weakest link, and that's one way to prove the theory is correct, by looking for dark matter, an invisible matter that holds the galaxy together. And we're clueless to understand what it's made of. But when we look at the proton and we say to ourselves, what is a proton made of? It's made out of 3 quarks. 3 quarks make up a proton. It seems to fit the data. However, when you try to calculate with quarks, no one has ever been able to extract out a proton out of 3 quarks, mathematically speaking. How do we do it in reality then? We do it by computers. Now, can you do it mathematically without a computer? We've tried. So far, nobody has been able to extract a proton by combining 3 quarks together. Now, it may turn out that subatomic particles are so complicated that no human can mathematically solve string theory completely. It may have to be done by computers, and that's where quantum computers come in. Quantum computers may ultimately settle the question, is there a theory of everything? And if so, is it string theory? Now, let me quote from a science fiction novel, The Restaurant at the End of the Galaxy. In that novel, a race of extraterrestrials decide to calculate the theory of everything. So they create a supercomputer that chugs and chugs and chugs to calculate the theory of everything. Well, after many eons of working on this problem, the computer announces that it's finished. It has finally found the meaning of the universe. And the meaning of the universe is 42. Well, you can imagine the disappointment. Is that all there is? Well, that's a danger. The danger is that maybe we do find the theory of everything, but it's not what we thought it was. Well, I think it should be incredible, fantastic, the culmination of all our work aiming toward a theory of everything. It should be fantastic. String theory is already fantastic, but maybe the next layer beyond string theory is an explanation for dark matter, black holes, and the universe that we see around us. Just waiting for a young, enterprising physicist to figure it all out.
Chapter 3. Are we in a simulation?
Ever since ancient times, people have asked the question, is the world a dream? Is everything around us an illusion created by some god to test us? Well, the modern version of that is this. Is the universe a computer game? Are we just dancing puppets in a computer game, obeying the laws of some computer someplace out there in the universe? Is everything basically a fake? Well, that theory got a tremendous boost with the Matrix series. Because in the Matrix, what we thought was real was actually a computer simulation. Is that possible? Well, the answer is probably no, but for a very sophisticated reason. If you want to simulate the weather, for example, you have to simulate the motion of trillions upon trillions of atoms. No computer is that powerful that it can simulate the motion of trillions and trillions of atoms that just make up the atoms in this room. You can't do it. And atoms are quantum mechanical. Atoms obey the quantum principle, so you don't really know where they are at any given point. So there's an infinite number of universes that are possible right in your room. It is mathematically not possible to create a fictional universe out of atoms in a fictional way. So sorry about that. The universe is not an illusion. Now, some people ask another question. What if the universe is an almost simulation? That's possible. Maybe you cannot simulate trillions and trillions of atoms because of something called the butterfly effect. Now, what's the butterfly effect? The butterfly effect is that when a butterfly flaps its wings, there's a certain small probability that the waves created by the butterfly will be magnified as it progresses, and eventually it becomes a storm. The point I'm raising is no computer is powerful enough to do that computation. The amount of information necessary to simulate atoms is absolutely staggering. You're talking about 10 to the, let's say, 25, one with 25 zeros after it, just to model the atoms inside a goldfish bowl. So we're talking about a fabulous amount of information necessary to create a model of a dream. So in other words, chances are we do not live in a computer simulation. Sorry about that. If you're a fan of the movies, you know that almost all the Marvel Comics movies are based in a parallel universe. And if you watch the Oscars, you find that the #1 movie in the Oscars is also based on parallel universes. And the question is, where did all this interest come from? It came from the quantum theory and string theory. This is one example of where advances in pure physics have helped to fertilize the entertainment industry, because the hottest thing in Hollywood today is the multiverse. So if you watch the Oscar-winning movie, Everything, Everywhere, All at Once, you have to realize that where did the idea come from? The idea comes from physics. And even today, we theoretical physicists are debating the question, how real are these parallel universes?
Chapter 4: Intelligent Life Beyond Earth.
What computers need is data, data by which we can draw conclusions. And when we talk about intelligence in outer space, we have to be open to the idea that their intelligence may be quite different from our intelligence. And therefore, the question is, how do we tell? How do we tell where real intelligence is, given the fact that there could be more than one type of intelligence? Well, let me give you an example. For the Science Channel, they once put me in a swimming pool with dolphins. Sensors picked up the squeals and chirps from the dolphins as I was swimming next to the dolphins, and then they ran it through a computer. The computer looked for regularities in the chirps and squeals of dolphins, realizing that they speak a totally different language than humans, and their criterion for intelligence would be different from our criteria of intelligence. So for example, the letter E is the most common letter in the English alphabet. And you can rank the frequency with which certain letters are used to pinpoint who wrote the article. For example, who wrote Shakespeare? Many people have claimed that other writers wrote Shakespearean plays, not Shakespeare himself, but you can run the set of information of Shakespeare's plays through a computer. And sure enough, the signature can be shown to be that of Shakespeare. The frequency of the letter E, the frequency of the letter I, and so on and so forth, allows you to pinpoint who wrote that article. So when you run the videotapes and the audio tapes of the dolphins through a computer, you find, bingo, yes, they are intelligent. Yes, there's a pattern, a regularity to their chirps, and so on and so forth. And then you go down the evolutionary scale. You go down to dogs, cats, rabbits, mice, insects. By the time you reach insects, it's pretty much nonsense. They have a communication system, but very little intelligence, other than to alert themselves for food, danger, and stuff like that. And so it is possible to rank intelligence using computers that look for an algorithm that allows you to see where intelligence lies. We'll do that in outer space now. We physicists have often wondered, are there signs of intelligent life in the galaxy? And if so, how advanced might they be? So we categorize these alien civilizations on the basis of energy consumption. Type 1 would be planetary. They control the weather. They control earthquakes, volcanoes, anything planetary they control because they have the energy of a planet. Then there's type 2. A type 2 civilization has exhausted the power of their planet, and they use the sun. They basically take the energy from their sun to power their machines. Sort of like the Federation of Planets in Star Trek. Star Trek would be a type 2 civilization. Then there's type 3, galactic. They roam the galactic space lanes. They play with black holes, sort of like the Empire of Empire Strikes Back. That would be a type 3 civilization. And then the question is, what are we? We are type 0. We get our energy from dead plants, oil and coal. We don't even rate on this scale. We have not attained planetary energy at all. That would be type 1. We're stuck at type 0. But what would it take to move between universes? What would it take to enter a black hole? What would it take to break the light barrier? You would have to reach the energy of type 3. And the energy of type 3 is called the Planck energy. The Planck energy is the energy of the Big Bang. It's the energy of a black hole. It's the energy, the greatest energy in the universe, and that is the Planck energy. How long before we can attain the Planck energy and move between universes? Well, a modest calculation shows that you would have to be about maybe 100,000 years more advanced than us in order to go between universes, to harness the Planck energy, to leave our universe. So chances are, if one day we meet an intelligent civilization, they would be maybe 100,000 years more advanced than us. Then the next question is, how would we know of a type 3 or type 2 civilization if we were to bump into one? Let's say that scanning the heavens, we see evidence of a type 2, type 3 civilization. How would we know? Well, we've looked. We've looked for type 2 because type 2 civilizations give off an energy, a characteristic black body radiation that we can measure. So far, we find none. Now, that doesn't mean that there aren't these civilizations out there. It just means that our devices are so primitive that we have not yet been able to conclusively show that they exist. But if they can break the light barrier, if they can go faster than the speed of light, then it's possible they may have the energy of a wormhole. And at that point, they would be type 3. They would have the energy, the Planck energy, to create universes or to move between universes. Historically, when physicists were asked about flying saucers and UAPs and extraterrestrial civilizations, the bottom line is data. You have to have data. You just can't say that, gee, I saw something going across the sky last night. Maybe you did, maybe you didn't. But now we finally have data. The United States Navy has admitted that, yes, there are hours of videotapes that can be analyzed to calculate the characteristics of these things. We now realize that these objects, whatever they are, can travel up to Mach 20 times the speed of sound. And they can accelerate from Mach 5 to Mach 20 very, very rapidly. And they can even fly underwater, believe it or not, underwater, in the air, into outer space. And they zigzag. When you calculate the centrifugal force inside the rocket ship, you realize that any living thing would be crushed by the zigzagging of these objects, whatever they are. We're talking about a new law of engineering beyond anything that we can muster here on the planet Earth. The ability to fly up at Mach 20, the ability to fly underwater, the ability to zigzag, these things require technology beyond anything we have. So we now have the data. Is it an optical illusion or is it extraterrestrial? We don't know until we analyze the data. And now we have physicists looking frame by frame and perhaps coming up with a conclusion as to where these objects come from. Well, about 90% of these sightings can be explained using natural phenomenon, or weather balloons, or weather anomalies, or meteorites. Most of them can be explained. 10% of them seem to defy the known laws of engineering, so we have to look at them very carefully. And some of them have multiple sightings by multiple modes. That's the gold standard. We met that gold standard on several occasions. Back in the 1980s, there was a JAL flight going across Alaska, and all of a sudden they found two objects flying next to it. These two objects were then tracked by radar, tracked visually, so there was multiple sightings using multiple modes. And then a third flying saucer came up next to it, so there were three objects now flying next to this JAL flight. Well, afterwards, when the flight landed, the pilots made the announcement that they saw a flying saucer, but then what happened? Very important. At that point, the pilots were given desk jobs, basically demoted. And that sent a chill throughout the industry, because if you say that you saw something unusual in your airplane, you would be given a desk job, and you wouldn't fly again. So in other words, keep your mouth shut. As a consequence, no data, very little data, has been collected until recently. And that's what we physicists need, data, so that we can make objective statements about what these things are. Now the burden of proof has shifted. The burden of proof is on the military now to prove that these things aren't extraterrestrial. And that's a sea change. Now we realize that we're sitting on hours of videotapes. We're sitting on a mountain of data. The data has to be analyzed frame by frame to figure out what these objects are, what their flight characteristics are, and who is behind them. So things have changed now. Now we have access to videotapes, and now the burden of proof is to prove that these things aren't extraterrestrial. What happened was citizens' pressure put pressure on certain politicians. These politicians, in turn, put pressure on the military to declassify some of this information. So that's how it happened. There is the FOIA Act, the Freedom of Information Act, that allows citizens to gain access to some classified information, but it's a long, torturous process. But some of it is now reaching the press, that yes, the military is owning up to the fact that it's sitting on a gold mine of data that has to be analyzed frame by frame.
Want to support the channel? Join the Big Think members community where you get access to videos early, ad-free.